No, because I teach pre-cal and I teach functions. And to me, it's a very clear distinction that there's probably not anybody in here that I'll be thinking of going to calculus next year from this class. That this is a stepping stone, if anything, to take pre-calculus or a class like that, whether it's here or somewhere else. So there are things I do in the pre-cal that I don't do in this class. And a lot of it is I don't do a ton of word problem kind of stuff in here that I would expect that they're doing. But this section is like all word problems. It's just pretty much the whole thing that there is. Most of the rest of this chapter, there was a little bit at the end of each section, but then this one is where it all gets concentrated into one. And the reason is because there's lots of exponential and log models out there in the real world. I mean, especially the exponential models. There just are. So it's practical stuff. I mean, some of it you've probably seen before in other classes. You've done radioactive decay, half-lives, and things like that in another class. Okay, well, we do the same thing here. If you've done any like population models in biology class or something like that, okay, that's the stuff here. I don't know, maybe would they do that in environmental science? Not sure. Okay, so at the beginning of this section, they present us with 5 models, 5 exponential and logarithmic models. And the first couple are fairly familiar. They are growth and decay. Right? Growth and decay. They don't look exactly the same as they did when we did it in the first section, because if you notice in the first section, when we first presented exponential functions, we actually wrote it like this: y equals a to the x, and that's it. Okay, that's not quite the model they're giving us here. They're giving us a now is a constant in front of an exponential, which has got a base of e, and then it's raised to the bx power, where a and b are constants. Right? They're not variables. They're just things we don't know as we start the problem. The fact that the b is greater than 0, positive, is why this thing is growth. But the model itself should look pretty familiar, right? That looks like our basic exponential function graph, right? It has an asymptote on the x-axis. It has a y-intercept of 1. It goes off towards infinity in the first quadrant. It's growing exponentially, right? Really fast. Right, the decay model, the only thing different in it is now the b has got a negative in front. The b itself, as we're saying here, the b is greater than 0, but there's a negative in front of it, so the exponent's going to be negative. Remember, when you put a negative in front of the variable inside the function, that's generally considered to be a flip across the y-axis, which is what this graph looks like if you compare it to the last line. That if you had data that you suspected looked like it could be modeled with an exponential function, you would probably put the data in your calculator, look at the scatter plot. It looks like it could be exponential. And then you could go to the calculator in the same menu that we use to do linear, quadratic, cubic, quartic. If you go to the bottom of that menu, the 0 option is for exponential. It does not give you that model. Right? It gives you something that looks like a times b to the x. So the a and the b will be constants that you're given through the modeling process. It won't give you a log base e. There's no way to force it into that kind of thing. But you could make an exponential model if you felt like that was what your data looked like. Okay, this one is it's not one that we can do much with. I'm going to show it. I'm going to explain it, but I'm not going to ask you to do anything with it. And you'll see why by the time we're done with it. But it actually could be the most practical of all these models that you see here, because that curve right there is the normal curve, right? It's the bell curve. That's what statistics, most of the statistics you use at not just the most basic level, but at any level, is based on normal curves. Normal curves are the result of random processes. You know, things like if I for 100 days timed how long does it take me to drive here, every day would be a little bit different because some days there wouldn't be traffic and sometimes I'd hit the light and some days I wouldn't. All those things are random inputs into the final outcome. But if I plotted the number of occurrences, you know, by their time, you would see that there's a peak in the middle, which is the average time it takes me, and then it would fall away to each side, kind of making the shape of a bell curve. And there's so many things you can consider to be the result of random processes. I mean, often the example they use here is like IQ, intelligence, an intelligence test, SAT scores. If you separate, let's say, males and females, height, you know, anything like that, it's got the shape of a bell curve. So that's a very useful curve. It just, there's not mathematically, there's not a ton we can do with it. Right, this is called logistics growth model. And logistics growth model, it's trying to show growth, but it's not the exponential growth that we're used to seeing, because what happens after it has that period of exponential growth, it caps itself and then kind of flatlines. It has an asymptote right here. So this thing has a period of exponential growth, but then it levels off. And I think logistics growth, there is a problem which I'm not going to do in our class, which they deal with exponential growth, and they deal with it in the context of a flu virus that is on campus. You know, the first person comes in with the flu, and he infects one person, right? And then that person infects one person. Pretty soon, they all affect a few, and pretty soon it grows really fast. But it's capped by, you know, first of all, the population that you're dealing with. At a certain point, you know, it stops growing because there's nobody left to infect. Which, when we talked about this in the pre-cal, you know, somebody said Ebola, right? But Ebola, you know, is not a contagious thing like the flu, so it wouldn't have the same kind of model as that. But just thinking about that, and this is just a little bit of a digression, I'll tell you that it reminded me of a flu. You know, there's a very famous flu that happened in 1918, which is known by the Spanish flu, right? It was right at the end of World War I. That flu killed up to 100 million people worldwide, 5% of the world's population. And, you know, the flu is something, you know, you really can. If a few of you had the flu, we'd all get the flu in here. It would pass that easily. And then you really do have to do quarantines. Ironically, where do you think the Spanish flu started? Not Spain, the United States. Haskell, Kansas. From Haskell, Kansas, which is a little town in southwest Kansas, it went to what's now called Fort Riley, Kansas, which is pretty close to where I went to college for the first 3 years. Those are my whole family's from. And, you know, that Haskell, Kansas got this thing, and it ravaged the town. Now, who knows why they got it? What were they doing there locally that created this flu? But they got this terrible flu, so bad that their doctor contacted the authorities and said, there's something really strange going on here. But by the time the authorities come out, they kind of plateaued. Everybody had gotten the flu. It was done, right? But in the meantime, America was just getting ready for World War I, and everybody was passing through Fort Riley. And so a few of those people get to Fort Riley, and now they get sent across the United States and eventually to France, to the trenches, and pass it to everybody. So that's what this kind of thing models. Okay, and then logarithmic models, right? Either base 10 or ln. In the end, they look pretty much like our log functions that we should be familiar with the shape of the graph. And again, you know, you can find a logarithmic model in the calculator. It's the option 9. It's the ln, right? It's the ln. If you want to have it as a log base 10, if it gives it to you here as an ln and you want log base 10, then use a change of base formula. Now you got log base 10. You know, in the homework problems they give us in this section, there's like almost nothing that's logarithmic. Everything is exponential. Kinsey? Nathan? You good? All right. So here's a typical kind of problem that involves an exponential model, right? And in this case, it's not like you got to refer back to the exponential model because they give you the model right here. Right? This is the one they want you to use. A and B are already filled in. Okay. So estimates of the amounts in billions of dollars of U.S. online advertising spending from 2011 through 2015 are shown in the table. There was a scatter plot associated with it, and then this model was arrived at. What does the 11 less than or equal to t less than or equal to 15 represent? Say again? It's the domain, right? They're telling you plug in values of t from 11 to 15. So where S is the amount of spending in billions and t equals 11 represents 2011. Compare the values given by the model to the estimates in the table, and then according to this model, when will the amount of advertising reach $80 billion? What are they asking you to do with this model? And they say, when will the amount reach $80 billion? When they say when, you know you're going to be solving for what? T, which is time, right? So 80 is the S, it's the spending. If they want us to substitute S equals 80, solve for T. Right? Substitute S equals 80, solve for T. Well, at that point, that's an exponential equation, kind of like we just solved in the homework last night. Follow the steps. Let me get my calculator. How do I solve this exponential equation? First step, isolate. In this one, what do I have to do to isolate? Divide by the 9.3, right? 80 divided by 9.3 equals e to the point 1129 t. Then what? Take the log of both sides. If nobody says anything, I'm just going to press and go faster, okay? That's just the way it goes. You could turn it into more of a back and forth, but if it's not going to be, I'll just press. ln of 80 over 9.3 equals ln of e to the point 1129t, right? But the ln of e to the point 1129t cancels. All you get is 0.1129t equals ln of 80 over 9.3. Divide by 0.1129. And that you can stick in the calculator. ln t equals 19.061. So what year would that be? 2019. Right? What's wrong with that answer? Because there is something wrong with that answer. What's the domain? Domain's 11 to 15. It doesn't go up to 19. Right? Which is kind of ironic. In the problem in the book, they don't say anything about that fact, that they just came up with an answer, which is not in the domain. And that's not unusual, that these kinds of things can happen. It's like in statistics, if I'm using my normal model to solve something, if the conditions for using it weren't quite met, it doesn't mean that you don't exactly use it. It means you use it with caution, right? We would be kind of hesitant to think that that might be the accurate prediction because it's not in the domain we were told is right. So that's not in domain. Right? Use with caution. So that's a pretty basic where, remember in the exponential growth model, there was a constant in front of the variable, right? And the constant is filled in already, right? The one step more difficult of that is the constant is not filled in, and that's what the next problem is. Right? In this problem, right, this is a population model, right? Again, you might have seen these kinds of things in another class. Populations in Tallahassee, Florida from 2005 to 2010 can be modeled by this right here. P equals 319.2 e to the kt. So we don't know the constant, which is in front of the variable, right? So we can't just plug in a value for p and solve for t, because there's two things we don't know up there, right? So whenever you get that kind of problem, you first have to find the k, right? How are you going to find k? You're going to find k because they have to give you a point where you know both the t and the p. You know the population at some point in time so that you can plug it in, and the only thing you won't know is k. Right? In this problem, you know that's coming, so then you read the next thing. Let's see. T represents the year with t equals 5 corresponding. I need Sam for the dean. Sam? Okay. Sam, let's go to the dean. Right. In this, they said t equals 5 corresponds to 2005. And then they tell us in 2006, the population was 347,000. Okay, there's your data point. You know the population for one point in time. That point would be 347. So plug it in, right? That'll be 347 equals 319.2 e to the 6k. And now you can solve for k. Again, using the same procedures. Isolate. Right? Take the log of both sides. I'm going to start that over here. That'll give us 6k equals ln of 347 divided by 319.2. Divide by 6. .0139. Okay, so now we know that this model is actually P equals 319.2 e to the 0.0139 times t. So we filled in the constant. So now we can answer the kind of question we did in the last one, if that's what they want. Okay. The next step says, use the model to predict the populations of Tallahassee in 2015 and 2020, which would mean, right, in 2015, t equals 15. In 2020, t equals 20. So plug in twice, right, 15 and 20, and calculate the p. That's just an evaluate at that point. Then you could also do like this one says, according to the model, in which year will the population reach 410? So they're asking you to do what? Plug in 410 in the place of p there. So we'll have 410 equals 319.2 e to the 0.0139 t. Solve for the t. Isolate. Take the log of both sides. Divide by 0.0139. 18.01. So that is 2018. And we didn't have any kind of domain statement or anything telling us that's not reasonable. Okay, well, I told you about those Gaussian models. You know, the Gaussian models are bell curves. In fact, this one is talking about SAT math scores. You know, you plotted all the math scores on a curve, right? And this is a frequency curve. You can see the most occurrences occur somewhere around the mean, you know, where you would expect the average score is on the SAT math. Now, you could see, you could put that function in the calculator and then use the calculator's, you know, maximum function to find the maximum point on the graph. And you can see they already did that. The maximum occurs at 514. So that's the average math score. Now, look into the equation here. Do you see the 514? It's right there. It's whatever is the value subtracted from the x. And you don't need to like put that in the calculator and use the maximum function to find that. You can see it right in the equation. The maximum will always be whatever number is being subtracted from x in the exponent. Right? It's being subtracted and then it's being squared. It's got a negative in front of it, which means this whole thing flips to the denominator. But when x equals 514, the whole exponent is 0. Right? And e to the 0 is 1. This thing has its maximum value when that happens. So anyways, you know, there's not much to do. Every one of the problems on this, all they ever ask for is what's the average? And they already gave you an equation which you could tell the average without going through that whole process. Right, these are the two homework problems. Right, this one is IQ scores, and they want you to know the average IQ score. So just looking at the equation, what's the average IQ score? 100, right? Which is, anyways, the way you define IQ, right? This one is the amount of time in hours per week a student utilizes a math tutoring center. Okay, what do you think is the average amount of time used per week? 5.4 hours. Right? It's right there. So to me, it's not very interesting to put that on the calculator just so we can find a value that we could tell before we started. So now I am going to give you a few of these. Right? I'm going to do the even ones here to show you how to set it up. And you'll do the odd ones for the homework. Okay, so this is continuous compounded interest. And we have a formula for that, don't we? What is the formula for continuous compounding? Right. A equals PE to the RT. So for every one of these problems, right, they're giving you a different amount of information and asking you to fill in the rest. For example, and your number 7 is going to be exactly like my number 8 that I'm doing right here. In this one, they're giving us the initial investment and the annual interest rate. Okay, the initial investment is the P, right? So they're giving us the P and they're giving us the R. Right, so let me plug that much in right here. A equals 750 e to the, and what do I put in as the interest rate if the interest rate is 10.5%? Remember, it's a decimal. You don't put in the 10.5, you put in 0.105, right? Move it over 2 decimals, 0.105 t. So that's what we know about this before we start, right? They want to know what is the time to double, right? So for time to double, that means how long will it take, we're solving for t, for the 750 to become double, which is how much? 1,500. So substitute double. Oh, yeah. And solve for t. Right? just like we've done in several problems so far, right? Isolate, take the log of both sides. Right? That is going to be how you do this one here. Right? How will you find the amount after 10 years? You know, if this is our model, you want to know how much is there in 10 years, then you plug in t equals 10. Right, and that will go there. We're good. Okay, let's say the number 10. Now we've got two different pieces of information. We've still got the initial investment. Now we've got the amount after 10 years. Okay, so let's see. What I can fill in for right away is I can say that A equals 500, because that's the initial, e to the RT. Right? I don't know the R. Right? R is a constant. I don't happen to know it yet. I've got to fill in for the constant here. So how can I use the other piece of information that they've given me to find the R? Well, the amount after 10 years is 1505. Right? That's telling you for one data point, right? When t equals 10, A equals 1505. Plug that in. And then again, that's an exponential model that you can solve for the R, the same way that we've solved already, right? Isolate, take the log of both sides. And then the time to double. Once you know what the interest rate is, right? Once we know what that is, then the time to double again, just substitute 1,000 for A, solve for the T. Right? Now, the fact is, you know, after the first two, which were definitely the even and the odd, were exactly the same. They gave you the same piece of information. The next four are all just a little bit different, right? There's none that have a repeat of the same information being given. Right? The next one, the number 12, they're giving us the time to double and the amount after 10 years. We don't know either one of the initial investment or the annual interest rate. Okay, so let's see. I'm starting with this. A equals PE to the RT. And I don't know any of the things in there yet, right? There's four things I don't know, A, P, R, and T. Right? Two of them are variables, but the other two are constants I don't happen to know as I start the problem. And I've been given two pieces of information, the time to double and the amount after 10 years. Well, just think. The amount after 10 years would allow me to plug in for which two letters? The A and the T. I would still have two things I don't know, right? That's not good. I can't solve for one thing if I don't know two things. But the time to double is a little bit different, because notice that if I divide both sides by P, if I make this A over P equals E to the RT, right? It doesn't matter what the initial investment was. right? If I doubled it, when I divide A by P, what do I get? 2, because I doubled it, right? I mean, I could, if it, like here, you know, when I doubled it, it was 1,000. You divide 1,000 by 500, you get 2, right? 750, it was 1,500. You divide 1,500 by 750, you get 2. It's always going to be that. It doesn't matter what the initial investment was. So that for this right here, the time to double, right, I can use that. 2 equals e to the, where am I at? Oh, 12 years, RT, so that is 12 times R, right? That, and then I can solve for the R, right? Then I'll know what the R is. I can go back up here and solve for R, or plug in the R, and then I can use this last bit of information, right? I can plug in for T and A and solve for P, right? So this solved for R, right? Once we know R, plug in amount A after 10 years, T, solve for P. Huh?
So whenever you divide A, or whenever you have A over P is equal to?
No, just if they're giving you the time to double, which that is, then we can say it's 2. It's not always, no. There's just one particular time where you know at the time to double, right? Yeah, what would that be if it was time to triple? 3, right? I mean, sometimes in these problems, they give you the initial amount, and then they ask you for the time to double, like we did in the first one, right? But the fact is, you don't really need to know the initial amount. Just the way it's going to work out, you don't need to know the initial amount. Because when you divide, you're going to get 2 or 3 or whatever is the multiplier. Okay, these problems, which I think most of you have done half-lives somewhere. Chemistry? Do you do half-lives in chemistry? And that's what these are like. This one, you actually do need to go back and get the model that they gave us at the beginning, right? What kind of model would we use for this? Decay, right? So you're going to go back. The model for decay is y equals AE to the negative BT, right? That's what you're using. So, and these are paired, right? The 22 and 21 are the same. You're going to do 21. I'm going to set up 22, same way you need to set it up. 23 and 24, exactly the same also. So let's see. For 22, the pieces of information we get are the initial quantity and the half-life. Okay. Which of these letters represents initial quantity? What does it mean, initial quantity? The amount at the beginning, right? At the beginning, what does T equal? 0, right? Before you start going forward in time, T equals 0. So this initial quantity means T equals 0. Well, if you plug in T equals 0, that means you have e to the 0, which is 1. And so the y equals whatever that a is. The initial quantity goes there. Right? Initial quantity, y equals 6.5. E to the negative b times t. Okay, now, what is a half-life? What does it represent? What is it? Is it a distance? Is it an amount of something? Is it a time? It's a time. It's the amount of time it takes for the initial quantity to become half of what it was, right? So this, if you start with 6.5, after 5,715 years, you'll have half of that, 3.25. That's what a half-life is. So it allows you to plug in for 2 quantities, right? The y and the t. So the only thing you won't know is the b. So let's do that. So we plug in here with the half-life. So I could say 3.25 equals 6.5 e to the negative b, so negative 5715 b. So at that point, you have an exponential equation, and you can solve it using the same old steps, right? Isolate, take the log of both sides. Right? Once you know the b, right? Once you know the b, you could plug in that here, and then if you want to know the amount after 1,000 years, right? Then you plug in t equals 1,000. First, you got to know the b. Okay. And then one more. If what we know is the half-life and the amount after 1,000 years, then we should be able to find the initial quantity. Okay, so again, we start with the same model, right? Y equals AE to the negative BT. And again, we're at the same point we were in the last set of problems, where now there's 4 things we don't know, right? And we need to figure out which one of these can I use to help me solve for one of them, right? If I plug in the amount after 1,000 years, that's going to give me a Y and a T, but I still won't know the A or the B. But if I use the half-life, right, in this case, I don't need to know what the initial quantity is. What I will know is that when I divide in the solving of this thing, when I divide the Y by the A, what will it be? 1/2. It's not doubling, it's 1/2. Right? So if you go Y over A, then that's 1/2 e to the, and the half-life is 24,100, negative 24,100 b. So using that same principle, I didn't write that in there right. Where we don't really need to know the initial quantity, because we know that we're going to, in the solvent, we can just use the Y over A equals 1/2 equals e to the negative 24. So solve for B. Right. Once you know the B there, then you can use the amount after 1,000 years, T and Y, solve for A. Okay. And that's it. That's the homework. You know, the first 5 are those last things I was just showing you, right? The third, this is the compound interest, this is the half-life. And the 29, 31 are word problems.